Every generation thinks it built the best one. On one side, steam, steel, and engineers who solved problems with fire. On the other, software, efficiency, and machines that outlast the people who built them. Classic or modern, steam or diesel, brute force or computing power. For 100 years, the railway industry has been having this argument. Let's settle it with the machines, not the opinions. Nobody asked for a bigger locomotive. In 1940, the Wasatch Mountains in Utah didn't care about requests. The grade at Wasatch was 1.14%, shallow enough to ignore until you were trying to haul 3,600 tons of freight up it at speed. Then it became everything. The Union Pacific needed a locomotive that could take a full train over that grade unassisted, no helper engines. One locomotive, one train, one crossing. What the American Locomotive Company delivered was the 4014. Wheel arrangement 4884. 4 leading wheels, 2 sets of 8 driving wheels, each set on its own engine articulated so the machine could navigate curves, 4 trailing wheels under the firebox, 25 wheels per side, 68 driving wheels total across the fleet of 25. Length 132 feet including tender. Weight 1,208,750 pounds fully loaded. That is 604 tons moving as a single unit. The boiler ran at 300 pounds per square inch. The firebox was big enough to burn coal, but Union Pacific ran the big boys on oil because Wyoming had oil and Utah had grades, and the math worked out in favor of oil. Tractive effort, 135,375 pounds. That number means something specific. It is the force the locomotive can apply to the rail before the wheels slip. 135,375 pounds of push at the point where steel meets steel. Produced horsepower, approximately 6,290. At the time of construction, no steam locomotive on Earth pulled harder. 25 were built, all delivered between 1941 and 1944, all assigned to the Ogden-Wasatch Corridor, all retired by 1959 when diesel made the grade argument irrelevant. 8 survive. 4014 is the only one still operational, restored by Union Pacific in 2019 after 60 years in storage, and it has been pulling excursion trains across the system ever since. The last working big boy. A machine that should be dead running. That is what 135,375 pounds of tractive effort looks like after 80 years. There are approximately 1,000 of these on the Union Pacific roster right now. The GE AC 4400CW is not glamorous. It was never meant to be. It was built between 1993 and 2004 to do one thing: haul freight efficiently across the American West, and do it reliably enough that the maintenance department would leave it alone. It succeeded at both. The AC in the name is not decoration. It refers to the traction motor type, alternating current versus the older DC motors in earlier diesels. AC motors can sustain full tractive effort at lower speeds without overheating. That matters on grades. That matters in the Wasatch. The prime mover is a GE 7F DL16 diesel engine, 16 cylinders, 4,400 horsepower at the prime mover, hence 4,400 in the name. That power drives a main alternator, which feeds the AC traction motors on each of the 6 axles. Maximum tractive effort, 145,000 pounds in starting mode. Continuous tractive effort, 109,000 pounds. The big boy's 135,375 pounds was a maximum figure. The AC 4400CW sustains 109,000 pounds continuously, hour after hour, grade after grade, without the thermal limits that constrain steam. Weight, 415,000 pounds, less than a third of the big boy fully loaded. 1 crew member instead of 3. Computer-managed wheel slip control. GPS integration on modern variants. Fuel efficiency measured in ton-miles per gallon, a calculation the big boys designers never needed to make. The AC 4400CW doesn't look like much. It looks like a box with trucks. but it has been hauling intermodal trains over Sherman Hill and Cajon Pass for 30 years, and it will be doing it for 30 more. The big boy was built because the mountain demanded something extraordinary. The AC 4400 CW was built because extraordinary isn't a business model.
The GG1 was not designed to be beautiful. Raymond Loewy made it beautiful anyway. The Pennsylvania Railroad came to Loewy in 1934 with a finished locomotive, all the engineering done, the machine functionally complete. What they got back from Loewy's pencil was something that looked like it had been poured from a single mold. The riveted external seams were gone, welded over. The cab profile was smoothed into one continuous curve from nose to tail. The pinstripes, 5 gold lines on Brunswick green, ran the full length of the body. It was a 460 plus 064 electric locomotive. 12 driving wheels in 2 sets of 6, articulated at the center. 2 cabs, 1 at each end, so the locomotive never needed to turn around. The catenary wire fed 11,000 volts of 25 Hz AC overhead. Onboard transformers stepped it down to run the motors. Rated horsepower, 4,620 at the rail. Later versions, 4,980. On January 27, 1953, GG1 number 4935 was hauling the Federal Express on the Northeast Corridor when something went wrong with the brakes. The locomotive came through Washington Union Station at speed and did not stop. It crashed through the terminal floor and dropped into the baggage area below. The locomotive was pulled out, repaired, and put back into service. That is the kind of machine the GG1 was. 139 were built between 1934 and 1943. They hauled troop trains in World War II, presidential trains, the mail, the milk, everything the Northeast Corridor carried for 40 years. The last GG1 in revenue service retired in 1981. By then, it had been running for nearly half a century. Top speed in service, 100 miles per hour. The locomotive that replaced it would need 40 years of infrastructure investment and a complete rebuild of American rail policy to match that number.
The Acela is the fastest passenger train in the Western Hemisphere. That sentence sounds impressive until you check the timetable. The Acela runs 457 miles between Washington, D.C. and Boston. It averages 68 miles per hour over that distance. This is because the Northeast Corridor, the most heavily used railway line in the United States, is shared with commuter trains, freight trains, and regional services, which means the Acela spends a significant portion of its journey running well below its top speed. The top speed is 150 miles per hour. It reaches that speed on exactly one stretch of track, a section in Rhode Island approximately 18 miles long. The Acela is built by Alstom, the same company that built France's TGV. The original Acela train set entered service in 2000. The next generation, Avelia Liberty, began entering service in 2021. It will eventually raise the top speed to 160 miles per hour on the sections of track that allow it. Power? Distributed. There is no separate locomotive. Traction motors are distributed under the passenger cars across the entire train set. Total output, 12,000 horsepower across the set. The ride is smooth. The interior is quiet. Business class seats recline. There is Wi-Fi. There is a cafe car. These are the specifications that actually drive passenger choice on the Northeast Corridor, because the alternative is Interstate 95. The GG1 held the corridor's speed record for 40 years. The infrastructure that limited it then limits the Acela now. 150 miles per hour, one stretch in Rhode Island, and an average speed that would have been recognizable to Raymond Loewy. The Acela is not a failure. It is a very good train operating on very old track. The track is the problem. It always was.
If you look at a photograph of almost any American freight train taken between 1972 and 1995, there is a reasonable chance the locomotive at the head of that train is an SD-40-2. The electromotive division of General Motors began production in 1972. The SD-40-2 was not a revolutionary machine. It was a refinement. A previous model improved systematically until every weakness had been addressed and every reliability issue resolved. The result was a locomotive that the railroads could not stop ordering. Thousands of horsepower, 6 axles, the 645 E3 prime mover, a 2-stroke turbocharged 16-cylinder diesel engine, truck-mounted traction motors, a design change from earlier locomotives that improved weight distribution and reduced maintenance costs. 18,566 were built between 1972 and 1986, 14 years of continuous production. Purchased by Burlington Northern, Union Pacific, Conrail, CSX, Canadian Pacific, and almost every other major railroad in North America. At its peak, the SD40-2 was the standard. It was what a freight locomotive was. It was not the fastest, not the most powerful, not the most technologically sophisticated machine available. It was the most reliable machine available at the best price with the best parts support. Railroads kept buying it because it did not give them reasons to stop. Many are still in service today, 50 years after the first units were delivered. That is the final argument for the SD40-2, not what it did when it was new, but how long it has kept doing it.
In 2004, GE Transportation released a locomotive specification that made 4,400 horsepower, ran cleaner than any freight diesel before it, and met EPA Tier 2 emission standards. They called it the ES44AC. Burlington Northern Santa Fe bought it in significant quantities. The ES stands for Evolution Series. The number refers to horsepower. The AC refers to the traction motor type. The critical change from the SD42 era is not the power increase from 3,000 to 4,400 horsepower. That matters, but it is not the story. The story is computerization. The ES44AC has wheel slip control managed by onboard computers monitoring each axle independently. It has load management software that distributes power across multiple units automatically. It has onboard diagnostics that identify mechanical issues and transmit data to maintenance crews before the locomotive returns to the shop. It has fuel efficiency systems that shut down idle engines automatically. The SD42 had a driver, a throttle, and a brake. The ES44AC has a driver, a throttle, a brake, and several 100,000 lines of software that manage everything the driver does not need to think about. BNSF operates approximately 700 ES44AC units. CSX, Norfolk Southern, and Union Pacific have comparable fleets. The Evolution Series is to modern American freight what the SD42 was to the 1970s, the default answer to the question of what a freight locomotive is. The SD42 solved reliability. The ES44AC solved efficiency. Between them, they defined the past 50 years of American freight.
Japan spent the late 19th and early 20th century importing railway technology from Britain and America, absorbing it, and then building something better. The C-62 was the end of that process for steam. Built by Hitachi, Kawasaki, and Keisha Seizo between 1948 and 1949, it was a 464 Hudson, the same wheel arrangement that American railroads had been using for their fastest passenger trains. The Japanese version was the most powerful steam locomotive ever operated in Japan. Tractive effort, 130,000 newtons. Weight of the locomotive alone, 88.8 tons. Driving wheel diameter, 1,750 millimeters, the largest ever used on a Japanese steam locomotive. The C-62 hauled the Tsubame and Hato express services between Tokyo and Osaka on the Tokaido Main Line, the same corridor the Shinkansen would later claim. At its fastest, the C-62 reached 129 kilometers per hour. That speed record for a steam locomotive in Japan was not broken until 1999. 49 were built. The last were retired in 1972. 2 survive in operating condition. C-62-2, maintained by JR Hokkaido, ran excursion service until 2013. A third, C-62-3, is a designated cultural property. The Tokaido main line that the C62 ran at 129 kilometers per hour now carries Shinkansen at 285 kilometers per hour. The trains are almost unrecognizable from each other. The corridor is the same. The S stands for Supreme. Japan Railways introduced the N700S in 2020 as the definitive evolution of the Shinkansen platform, the platform that has been running on the Tokaido line since 1964. The original Shinkansen ran at 210 kilometers per hour. The N700S runs at 285 kilometers per hour on the Tokaido line and 320 kilometers per hour on the Sanyo line to Hakata. The nose is 10.7 meters long, not for aesthetics, for aerodynamics, specifically to manage the pressure wave generated when the train enters a tunnel at 285 kilometers per hour. In the original Shinkansen era, tunnel entry at speed caused a sonic boom at the tunnel exit. Lengthening the nose solved it. The distinctive duckbill profile is an aerodynamic solution to a physics problem. The N700S weighs 700 tons for a 16-car formation. Distributed power. Every car is a motor car, all 16 of them, a total of 17,080 kilowatts across the full set. That is approximately 22,900 horsepower. Active suspension. Lithium-ion battery self-propulsion system for emergencies. Dampers to control earthquake-triggered oscillations. The N700S is the safest high-speed railway system ever operated. 0 passenger fatalities in over 60 years of Shinkansen operation. The C62 hauled the Tsubame Express at 129 kilometers per hour. The N700S now covers the same Tokyo-Osaka journey in 2 hours and 22 minutes. The corridor did not change. Everything else did.
8 locomotives, 100 years of the same question, answered 8 different ways. The big boy moved 600 tons over the Wasatch with brute force. The AC 4400 CW does it with software and 145,000 pounds of starting tractive effort and a maintenance crew that doesn't need to be there. The GG1 ran the Northeast Corridor for nearly 50 years and looked extraordinary every day it did it. The Acela runs the same corridor now, faster in theory, slower in practice, on the same infrastructure Loewy's locomotive helped justify building. The SD40-2 was the most reliable machine American railroading ever produced. The ES44AC is the most efficient. They are not the same complement. And the C62 climbed to 129 kilometers per hour on a line that now carries 285. The N700S nose is 10.7 meters long because of the physics of what happens when something that fast enters a tunnel. The C62 never had that problem. Better is real. Progress is real. But something else is also real. You cannot look at a GG1 on the Northeast Corridor and tell yourself that what replaced it is more beautiful. Some things got faster, some things got cleaner, some things got better, and some things were just more alive.